So in this lecture, we're going to learn about the Hamilton-Jacobi theory. So we've learned about canonical transformations, and the Hamilton-Jacobi theory is one special case of such canonical transformation. So we're going to see what that is about. So we said in our canonical transformations, we start with the initial coordinate system QP of phase-space system, small q, small p. And from here, using a generating function that generates this transformation, we go to a new set of coordinates, capital Q and P. Okay, so capital P. So hope that is differentiated. So this is small p and this is capital P. And this is the generating function that generates this transformation. Now, in the Hamilton-Jacobi theory, what we're going to say is this generating function is going to transform the coordinates from Q to P to new coordinates, where these new coordinates are actually Q naught and P naught, which means these are the initial conditions. That is, this is the position, this is the value of Q at time t naught and the value of P at time t naught. So we're going to generate such a transformation, and how we are going to do that is that we're going to demand that the new Hamiltonian is, we said this is the old Hamiltonian, right? K, H, and the new Hamiltonian, we're going to demand that this new Hamiltonian is actually 0. So we're going to look for such transformations wherein we transform the new coordinates are actually the initial conditions of the system. So, and then we'll see how we can obtain the equations of motion using such a transformation. So, as I said, the condition here is that the new Hamiltonian is 0, right? So the equations of motion, the Hamilton's equations of motion, this is what the Hamilton's equation of motion says, that Q dot is equal to dk by dp, and we are saying that the new Hamiltonian, we are demanding that the new Hamiltonian is 0, so therefore Q dot will be 0. And this is the other set of, so P dot also will be 0 because K is 0. Now we're going to use the generating function of the type F2. So in our previous class about canonical transformations, we had seen about 4 different types of generating functions. So we're going to use the generating function F2. Okay, so F2 is a generating function of variables Q, small q, capital P and T. Okay, so this is the generating function we are going to use. And we had worked out how the transformations work out, right? In our previous class about canonical transformations, we had worked out for each generating functions what are the transformations that work out. So here the old Hamiltonian and new Hamiltonian are related by this equation, and we have the old momenta is related by this equation, and also the new coordinate is related by this relationship, so capital P. So these are the relationships. So we're going to give a special name to this generating function because we are using it in this theory. It's going to be called the Hamilton's principal function. Okay, so this is going to be called S. Okay, so new designation, and it's going to be called Hamilton's principal function. And notice it is going to be a function of Q, right? And what is P? Since P dot is a constant, that means P dot is 0, right? So p dot is 0, therefore p will be a constant, right? So if some derivative of something is 0, if I say dx by dt is 0, then that means x is equal to a constant, right? So that is what we are saying. So this is going to be a function of q's alpha, some constant, okay, the new constant momenta, and t. So this I will call Hamilton's principal function. Hamilton's principal function. Okay. So what we have is, as I said, p, the new momenta is obviously going to be a constant, right? It's going to be a constant, and the new coordinate also by this equation, the new coordinate we have said that q dot is 0, therefore q will be a constant. So the new coordinate q is going to be some constant beta, and it is nothing but ds by d alpha. So it all comes from these relationships for this type of generating function. So now we can easily solve for the equations of motion in terms of alpha and beta. So q will be a function of alpha, beta, and t, and p will be a function of alpha, beta, and t. So this is just telling you that your equations of motion of the system are going to be just functions of your initial uh, momenta and position and time. Okay, so we just arrive at the solution easily like. So this gives the time evolution of your q and p in terms of the constants q naught and p naught. That is the initial position and the initial momentum. So when we apply this to some problem, these concepts will become more clear to you. Okay, so when we are going to do that, we're going to use this theory and solve the linear harmonic oscillator. The harmonic oscillator problem, we're going to do that. That will be in the next video. So hope you understood this. If it's not clear, look at the next video, which is going to be a problem based on this theory, and that will be more clear to you.